Have you ever stopped to think about the technology all around us? So much of it feels like magic. Well, today we're going to pull back the curtain on the invisible physics that makes it all work. We're going to tackle a few everyday mysteries that are actually just the super elegant rules of waves doing their thing.
I mean, seriously, think about it. You pop on a pair of noise-canceling headphones, and the drone of a plane engine or the buzz of a coffee shop just disappears. How is it possible to add something, a pair of headphones, and get nothing?
You've definitely been there, right? You can hear that thump, thump, thump from next door clear as day, but you can't make out the lyrics or any of the higher notes. So what's the deal? Why does the bass get a special VIP pass straight through the walls? It's such a classic movie scene, but is there any truth to it? How could listening to a solid chunk of steel possibly tell you a train is coming better than just listening to the air around you? Yep, that's the single thread connecting all of these seemingly random things. It's not magic, it's just waves. And you know what? Once you get the hang of a few basic rules, you're going to start seeing them absolutely everywhere.
Okay, so let's start with the absolute core idea. A wave. What is it? Imagine you toss a pebble into a pond. You see the ripple spread out, right? That ripple, the disturbance, is moving outward, but the water itself is pretty much just bobbing up and down in the same spot. The energy is traveling, but the stuff is staying put. That right there is a wave.
And every wave has like a basic toolkit, 3 key properties. First is amplitude. That's just its power or strength. For sound, we experience that as loudness. Then there's frequency, which is how fast it's vibrating. We hear that as pitch, the deep thump of a bass drum versus the high pitch of a whistle. And finally, wavelength is just the distance from one peak of the wave to the next, and it's tied directly to frequency.
Now, most waves, like sound, are what we call mechanical. They need stuff to travel through. We call that stuff a medium: air, water, a solid wall, whatever. But, and this is a huge but, electromagnetic waves are the exception. Things like light, radio waves, your Wi-Fi signal, they're special. They don't need any medium at all. That's how we can get sunlight and radio signals from space probes through the total vacuum of space.
All right, get ready, because this next idea totally flips a common myth on its head. We usually think of sound traveling fastest through wide-open, empty air, right? Well, it's actually the opposite. Think of it like a bucket brigade passing along a bucket of water. In the air, the particles are all spread out. Passing that energy bucket is slow and sloppy. But in something dense and stiff like steel, the particles are packed in tight, shoulder to shoulder. The handoff of energy is nearly instant. That's why sound travels about 15 times faster through steel than it does through air. So, with those basics under our belt, we can start to piece together the clues to our mysteries. And the first big one is a behavior that all waves have. It's called diffraction, or as I like to call it, the around-the-corner rule. See, when a wave hits the edge of an obstacle, it doesn't just stop, it bends. But here's the trick: not all waves bend the same. Low-frequency waves, like the bass from that party, have these long, lazy wavelengths. They can curl around corners and through openings really easily. But high-frequency sounds, like a singer's voice, have short, tight wavelengths that tend to travel in straighter lines, more like a beam of light. They get blocked much more easily. And that's it. That's the solution to our party mystery. It really is that simple. The low notes literally bend their way through and around the wall to reach your ears, while all the higher notes get stuck.
Okay, on to our second clue. This one is about what happens when 2 waves meet. You might think they'd crash into each other like billiard balls, but they don't. They actually pass right through one another. And for the moment they're in the same spot, they combine. We call this interference.
And this is exactly the trick that noise-canceling headphones use. It's a brilliant, super fast 3-step process. Step 1, a little microphone on the outside listens to the annoying sound wave coming in. Let's call it shape a peak. Step 2, a tiny computer chip instantly creates the perfect mirror image of that wave, a trough. Step 3, the headphones play that new trough wave into your ear at the exact same time the original peak wave arrives. The peak and the trough meet, they perfectly cancel each other out, and the result is silence. It's not magic, it's just math.
All right, we have our toolkit now. We understand mediums, we know how waves bend, and we know how they can interfere with each other. So let's put it all together and officially solve the mysteries we started with.
So that train on the tracks mystery? It's a perfect example of our bucket brigade rule. Sound is just a vibration traveling through a medium, and that vibration travels way, way faster and more efficiently through the dense, stiff, tightly packed particles of a steel rail than through the spread out particles of air. That's why putting an ear to the track really works. The sound of the train arrives through the rail long before you could ever hear it through the air.
So we've cracked our cases, but it kind of brings up another question, doesn't it? We know sound travels, but why does it fade away so fast? It's not just about getting farther away. There's a really specific and cool law of physics at play.
It's called the inverse square law. But forget the fancy name. The easiest way to get it is to stop thinking of sound as a beam and start picturing it as an expanding bubble of energy, radiating out from the source in every direction, kind of like a balloon being blown up.
Now let's say you're standing right here, and then you take a few steps back so you've doubled your distance from the source of the sound. By doubling the distance, that original bubble of sound energy has to stretch itself out to cover a surface area that is now 4 times larger. And here's the payoff. You've got the exact same amount of initial energy, but now it's spread out over 4 times the area. So the intensity, what you actually hear, is only 1/4 as loud as it was before. The energy just gets diluted by spreading out through space.
So, okay, sound gets diluted by distance. But does it just go on forever, getting infinitely weaker? Nope. There's one last rule that explains why all waves eventually, run out of steam.
It's called attenuation. As the wave makes the particles in the air vibrate, there's a little bit of friction happening between them, and that friction converts a tiny piece of the wave's energy into a minuscule amount of heat. In engineering, you might hear this called signal damping. So the energy doesn't just disappear, it actually changes form, and over a long enough distance, the wave just fades into nothing.
So let's wrap this up. You've basically just gained a new superpower, a kind of physics X-ray vision. You know now that sound actually prefers the express lane through solid objects. You know exactly why you hear bass around a corner. You know that noise canceling is just incredibly clever and fast wave math, and you know why sounds fade away so quickly.
Now that you have these rules in your head, the world might start to look a little different. So I'll leave you with this final thought. What other things in your daily life, what other bits of technology that feel like magic, are really just wave physics hiding in plain sight?